Okay, we're now going to look at the last of our properties of the Laplace transform, namely the final value theorem. This is a property that's very useful when we're analyzing and designing control systems, as you will do in SE 380. We've already seen the initial value theorem, which let us found the value of f of t as little t went to 0 from above, without inverting the Laplace transform f of s. So we could find it from f of s without inverting f of s. Similarly, this final value theorem will let us find the value, the limit of f of t as t goes to infinity, if it exists, from the transform f of s without inverting that transform. Some conditions have to be satisfied in order for it to hold. So we'll let f of s be a proper rational function. And we have to state some conditions on the locations of its finite poles. Its poles all have to lie to the left of the imaginary axis, or in other words, the real parts of its poles have to be strictly negative, except that it can have a single pole at the origin of the s-plane at s equals 0. So with the possible exception of a single pole at s equals 0. And in fact, we can be a bit more general than this. As we've seen, our transforms are typically either rational functions or rational functions multiplied by complex exponentials. So f of s can, in fact, consist of a rational function like the one we've just been talking about, satisfies the conditions we've just given, multiplied by a complex exponential. So say an exponential of the form e to the s capital T. So under this condition on the poles of the rational function, the limit as t goes to infinity of f of t, what we call the final value of little f of t, can be found from the transform by taking the limit as s goes to 0 of s times f of s. So we're again taking the limit of this quantity s times f of s, just as in the case of the initial value theorem, but now it's the limit as s goes to 0, instead of the limit as the real part of s goes to infinity. Intuitively, the final value theorem is useful for analyzing the steady state behavior of systems, the limit as t goes to infinity. And as the final value theorem says, steady state behavior really all depends on what happens as you approach the origin of the s-plane. Thinking of s as a kind of abstract frequency, it's as the frequency goes to 0. That's what tells you what happens to the system in steady state. We can say a little bit more. If the poles of the rational function do not satisfy the conditions, then the final value does not exist. So in other words, the limit of f of t as t goes to infinity does not exist. And we'll actually go through the proof of this final value theorem so that you can understand things in detail. So the idea is that when it applies, this theorem lets us calculate the final value, the limit of f of t as t goes to infinity, without inverting the transform f of s. What we do have to do in order to find the final value is take the limit as s goes to 0 of s times f of s. And we should be a little bit more precise about what this means. In this case, we're using the sort of standard definition of the limit of a function of a complex variable. Here's that definition. Suppose we have a function g of z, where z is a complex variable. Has a limit, lambda, in the complex numbers, as z approaches some value z naught. If it's a standard sort of epsilon delta definition, for every epsilon greater than 0, there exists a delta greater than 0 such that the modulus of g of z minus lambda, or in other words, the distance from the point g of z on the complex plane to the point lambda on the complex plane, is less than epsilon whenever the distance between z and z naught is less than delta. Okay, so this means that you can be sure that the difference between gz and delta, or the distance between those gz and lambda, or the distance between those 2 points on the complex plane, is less than epsilon as long as the distance between z and z naught is less than delta. So this means that the closer z gets to z naught, the closer g of z gets to lambda on the complex plane. So this is the standard definition of a limit on the complex plane. So in a sense, it doesn't matter what direction z is approaching z naught from. As long as z gets closer and closer to z naught, g of z will get closer and closer to lambda intuitively. So that explains the right-hand side of the equation in the final value theorem. So just again, it says, the final value theorem says, under all of our assumptions, that the final value of f of t is equal to this limit of s times f of s as s goes to 0. So let's look at some examples. Suppose f of s excuse me, is s over s squared plus omega squared. Then the limit, as s goes to 0, of s times f of s equals the limit, as s goes to 0, of s squared over s squared plus omega squared. So that's going to be 0. Okay. It's not too hard to see. You can apply our epsilon delta proof if you like. So does our final value theorem apply in this case? Well, note that in fact this is where omega is real. We're assuming omega is real here. In that case, this denominator in fact has imaginary roots. So f of s has poles that lie on the imaginary axis. Their real part is equal to 0, not strictly less than 0. And if omega is greater than 0, then they do not lie at the origin. So in fact, the conditions of the theorem are not satisfied. And we'll see that, in fact, the final value of f of t does not exist. Because if you invert this Laplace transform, you get cos omega t, or cos omega t times the unit step, if you like. Let me write it that way. So the limit as t goes to infinity of f of t does not exist. And in fact, that's what our theorem says. If the conditions on the poles of f of s are not satisfied, and they're not satisfied in this case because there are non-zero poles on the imaginary axis, then the final value of f of t does not exist. Intuitively, that's because these non-zero poles on the imaginary axis correspond to terms in the inverse transform that are trigonometric functions, cosines and sines. So the limit as t goes to infinity of f of t does not exist. So this actually agrees with the final value theorem, which said that if the conditions on f of s aren't satisfied, then that final value does not exist. Let's take a look at another example. Suppose f of s is 10 over 5s plus 1 times 1 over s. And in fact, we've seen examples like this. We saw an example of inversion of a transform like this. So first of all, this satisfies the conditions on the poles of f of s. So this should let us calculate the final value of f of t by computing the limit as s goes to 0 of s times f of s. And that's just going to be the limit as s goes to 0 of 10 over 5s plus 1 So this limit is just going to be 10. And in fact, this checks out. Without going through the whole the whole inversion of the transform, you can see that this will be the case. Well, let's just check that. Make sure I haven't made a mistake. So this should be we should be able to express f of s as a over s plus, say, b over 5s plus 1, or to put it in a more common form, we could say s plus 0.2. If you divide through by 5, then this function becomes 2 over s plus 0.2. So what do we get for our constants a and b? By the Heaviside cover-up, we get that a is equal to what we get by multiplying through by s, or in other words, by covering up the s in the denominator of f of s, and letting s go to 0. That means a is going to be equal to 10. And we can find b in similar fashion. If we multiply through by s plus 0.2, then in fact this term here is going to come out to be equal to 2. And then as we let s tend to minus 0.2, we are going to get 2 times 1 over 0.2 equals 10. And in fact, we didn't really need to find the value of b, because we know that the inverse transform of the second term in our partial fractions expansion is going to be a decaying exponential, right? It's going to be the constant b times e to the minus 0.2t. So as t goes to infinity, this is just going to decay to 0. But the inverse transform of this first term will be a times a unit step. So the final value of that term will just be a, which is 10. So indeed, the final value of the inverse transform of f of s will be 10. Roughly speaking, we could say that the plot of f of t in this case looks like this. It consists of a step. Let me we let s equal minus 0.2. Yeah, s equals minus 0.2, so in fact we have a minus sign here that I left out. So in fact, the function looks like this. It exponentially converges towards the final value of 10. So that's an example where the final value does exist. And we see that the result, the conclusion of the theorem is in fact correct. This example should give a pretty good idea of the proof of the final value theorem. In fact, these two examples together give a pretty good idea of the proof. Let's just go through the proof. First of all, note, you might wish to check this out by doing a case analysis, that if the conditions on f of s are not satisfied, then the limit as t goes to infinity of f of t does not exist. Why is that? If those conditions are not satisfied, then either f of s has a pole whose real part is either 0 or positive, so its real part is non-negative. And in fact, either that pole is not at the origin or there's more than one such pole at the origin. So if the real part of a pole is non-negative, then you should be able to see that, well, let's look at some of the cases that you want to consider. So suppose the real part of a pole is 0, but the imaginary part is not 0. In that case, as we saw from the first example, there will be sinusoidal terms in f of t. And the limit of those sinusoidal terms as t goes to infinity will not exist. Suppose, again, that the real part is 0 and the imaginary part is 2. Then it's all right if there's one such pole, but if there are multiple poles at s equals 0, then f of t, if you like, let's just say contains f of t contains positive powers of t. For instance, suppose there are two poles at the origin. Then in the partial fractions decomposition of f of s, there's a term that's a constant times 1 over s squared. 1 over s squared is the transform of t to the power 1 multiplied by the unit step. If you have 1 over s cubed, then you've got a parabola, a parabolic term, a quadratic term in t, and so forth. So as t goes to infinity, these terms are going to blow up. And if there's a pole whose real part is positive, then you know that there is a term in f of t, which you can see by considering partial fractions decomposition, that is going to have a factor that is a growing exponential. Let's just say f of t contains a term whose absolute value grows exponentially with t. On the basis of the partial fractions decompositions and inversions that you've already done, you should be able to understand these three cases. And that's why those conditions on the positions of the poles of f of s have to be satisfied in order for the final value of f of t to exist. So that's one part of the proof, or at least a sketch of one part of the proof. Now, for the rest, suppose that the conditions on f of s and its poles specifically are satisfied. Then consider a partial fractions decomposition of s. Of f of s, rather, sorry. It's going to have the following form. First of all, if there is a single pole at the origin, it'll have a term that's a constant a divided by s. And it'll have other terms of the form b over s minus, say, p sub I to some power k, some non-negative power k, some positive power k, where the pi have real parts that are strictly negative. In that case, you know that all of the inverse transforms of these terms are going to be exponentials of the form e to the power pit. And by virtue of the fact that the real part of pi is strictly negative, those will be decaying exponentials. So the inverse transforms of these terms will all go to 0 as t goes to infinity. So you'll be left just with the final value of the inverse transform of this term. Well, this, of course, is a times a unit step, so its final value is going to be a itself. So it follows that the final value that we're looking for but what is the value of a? Well, again, we normally evaluate these constants, or these residues as they're sometimes called, in partial fractions decomposition by using the Heaviside cover-up. And in this case, because a is the constant that goes over the denominator s, the method of the Heaviside cover-up is essentially to multiply both sides of the equation by s. So in particular, the one side of the equation will just be s times f of s, and then let s go to 0. And we know that in the decomposition will then just tend to a, and the right-hand side will be the limit as s goes to 0 of s times f of s. But that is precisely the value that we're after, because the final value of f is a itself. So it's really a result of the Heaviside cover-up, if you like. The Heaviside cover-up tells us that if the conditions on the poles of f of s are satisfied, then the only term in the inversion of the transform that does not go to 0 as t goes to infinity is going to be the inverse transform of this term, and its final value will just be a itself. By the Heaviside cover-up, a must be the limit as s goes to 0 of s times f of s. So that's the last of our Laplace transform properties. And in the notes, you now have a table of all of the 9 properties of the Laplace transform that we've looked at. Now, we could earlier on have started applying the Laplace transform to the solution of initial value problems, which is sort of what the first part of the course is all about, what motivates the first part of the course. We could have started doing that as soon as we covered property 6, which concerns differentiation and integration. So in the final lecture for this week, we're going to go back and do that. We'll go back and apply the Laplace transform to the solution of initial value problems. See you in the next lecture.